purpose of this video is to go through the questions on diffraction that were set last week for the A-level physics students. Now you can go as fast or as slow as you want. There may be other ways to solve the questions, but I've gone through the process that I think will best allow you to get the answers based upon what we've been learning in class. So if we look at question 1a, explain why the signal strength falls to a minimum between B and C and D. As you can see, we've got a double slit, microwaves, electromagnetic radiation, and we can see that we've got that microwave receiver moving from position A to E, I think, if memory serves me right. So look at the question, hopefully. Yeah, along the dotted line A to E. Okay, and we've got the slits, and we've got the slit distance. Okay, this bit about polarized is going to be important later on, but at the moment we just need to be aware of how it's moving. Right, moving on. So what we need to see here is that we're going from a maximum to a minimum. So we've got constructive and destructive interference, but we're going to look at the path difference of two waves. So for the path difference, we're going to use the information we're given about S1 and S2, as you can see in the diagram. What that does is it gives rise to a phase difference, and that phase difference, okay, is if it's 180 degrees exactly, then we're going to get pi radians, and it's going to be complete destructive interference occurring. But we're not getting that. Okay, we're getting a minimum. It doesn't say that it goes down to zero, it goes to minimum. So what that's saying is that there is a phase difference, but that phase difference isn't 180 degrees or pi radians or half a wavelength out of sync completely. The phase difference isn't quite there, so there is a minima. There is some destructive interference reducing it, but not completely. So those are the key points for that answer. Path difference, phase difference, okay, and destructive interference, which isn't a completely in phase or 180 degrees phase difference. Right, the frequency of the microwaves that are transmitted in question 1b. So we've got S1 and we've got S2, and those units are in meters. That gives us a path difference of 0.056 meters. So if we're looking at D is at the maximum. Point D is at the maximum. Therefore, it is a constructive, and it's the second order maximus. So the path difference at those locations are two wavelengths exactly. So therefore, the wavelength is going to be 0.028 meters. Using the wave equation, we can then put our values into that, and we can get a frequency of 11 times 10 to the 9 hertz, 10.7. Okay, so 1c, the intensity of the waves passing through each slit is the same. Explain why the minimum intensity between C and D is not zero. Well, I've sort of explained that already. Maximum and minimum signals are detected, not zero signal. So we're not getting a perfect destructive interference. We are getting perfect constructive from the information that we're given. And the intensity of the waves passing through each slit is the same. So therefore the intensity decreases with distance. One wave travels further than the other. And the amplitudes and intensities of the waves at the minimum point are not equal. Therefore they do not cancel out each other. 1d, the vertical aerial is placed at position B and is slowly rotated through 90 degrees until it lies along the direction AE. So if we think back to that diagram, we've got a vertical aerial, and we're going to move that through that. This is where the information about polarization becomes really important. So the thing that we need to think here is that the microwaves from the transmitter are polarized. Okay, and they are detected by the aerial in the microwave receiver, so therefore they must be orientated vertically. Okay, so the waves are polarized along a vertical plane. So when we move towards the horizontal, which is what the question's asking you, that's what we're getting to start with. So the antenna will pick that up, or the aerial will pick that up, no problem, like that. If we now move it through 90 degrees, okay, what we'll get is the same as we did when we were looking at the polarization with the ropes in the classroom. We can see that we'll get no transmission happening at that point. So the answer I would answer as the waves transmitted are polarized, so the signal decreases, becomes zero, and the signal will reach zero when the detector is at 90 degrees to the transmitting aerial, or the direction of the polarization of the wave. So those are the 3 points for the answer. Okay.